We are in topic 3, Statistical Inference, focusing on confidence interval.
The core objective of inferential statistics is ambitious, drawing mathematically rigorous conclusions about entire populations, even though we can never observe every individual data point. Since surveying millions of instances is practically impossible, we have to extract a smaller, representative sample from that larger whole. From this subset, we calculate the sample mean, denoted as x bar, acting as our logical estimate for the unseen population. The point estimate stands alone. It contains no built-in metric to communicate its own margin of error, making it impossible to gauge our true accuracy. To solve this, we have to abandon the illusion of perfect precision and instead construct a mathematical net. By expanding outward from our point estimate, we create an interval estimate. This is a computed range of values designed specifically to capture the true parameter, while mathematically acknowledging our own uncertainty. To map real-world data effectively, we leave the fragile point estimate behind and use the bounded parameters of an interval. Constructing an interval requires us to assign it a confidence level. This is the exact metric that dictates how reliable our calculated range actually is. But we must correct a widespread professional misconception. A 95% confidence level does not mean there is a 95% probability that your specific interval contains the true mean. The population mean is a fixed reality, not a variable. It is either inside your brackets or it isn't. This animation illustrates the strict frequentist definition of confidence. It evaluates the behavior of our estimation process when repeated over a large number of drawn samples. If we extract 100 unique samples and compute an interval for every single one, the confidence level dictates the success rate. Here, 95 intervals successfully intersect the true population mean. 5 of them miss entirely. We place our trust in the overarching methodology, not the luck of a single draw. Once computed, the interval has already succeeded or failed. Therefore, a 95% confidence level is simply a mathematical guarantee that our process will capture the true parameter 95 times out of 100 over the long run. This curve represents the standard normal distribution, which serves as the foundation for constructing our interval formula, specifically for scenarios where the population's standard deviation is already known. We begin with the variable alpha, which dictates our total acceptable error rate. This error is visualized in the extreme scales of the distribution curve. Because our interval stretches symmetrically above and below the point estimate, we divide alpha by 2, allocating the acceptable error equally to the left and right tails. The exact boundary line where the acceptable error tail begins is marked by a critical value, denoted as z sub alpha over 2. These critical values correspond to fixed statistical benchmarks. For a 90% confidence interval, the critical value sits precisely at 1.65 standard deviations from the center. Expanding our requirement to 95% confidence pushes the boundary outward to a critical value of 1.96. And requiring a 99% confidence level pushes the z-value out to 2.58, leaving almost no room for error in the extreme tails. Notice the structural trade-off. Demanding a higher level of statistical confidence mathematically forces you to accept a wider and therefore less precise interval. By combining these variables, we assemble the complete confidence interval formula. We take our point estimate, x bar, and subtract and add the critical value, multiplied by the population standard deviation over the square root of the sample size. This entire cluster on the right side of the plus-minus operation is formally defined as the margin of error. It dictates the maximum expected mathematical distance between our sample mean and the true parameter, governed strictly by the confidence level we selected. Inferential formulas are not automated reality generators. They are logic constructs that only work if strict mathematical assumptions are met before the calculation even begins. If the underlying data violates these base assumptions, the resulting interval is mathematically invalid. First, data must be gathered via random sample to avoid systemic bias. Second, sample size must be at least 30, unless the population is normal. Watch how this distribution curve behaves. This visualizes the central limit theorem in action. Once the sample size crosses the threshold of 30, the distribution of sample means smooths into a normal curve, regardless of how heavily skewed the original population was. Without verified random sampling and adequate size, computing a z-interval offers nothing but a dangerous false sense of certainty. But there is one final issue with the formula we built. It assumes we already know the population standard deviation. In practice, if conducting inference because the population mean is unknown, it is incredibly rare that you would already possess the true population standard deviation. When that exact parameter is missing, the standard normal distribution fails to accurately bound our error, and the z-formula breaks down. This missing information forces us to pivot to a different, more adaptable statistical tool. We must swap the z-critical value for a t-value, and the population standard deviation for the sample standard deviation. While the z-interval provides the necessary conceptual architecture, it is the t-distribution that equips us to analyze the messy, incomplete reality of field data.
Thank you. Disclaimer. Artificial intelligence, AI, was used in the development of selected instructional materials in this lesson. The use of AI is intended to enhance clarity, visualization, and learning engagement, while all academic content has been reviewed and guided by the instructor.